Hello, everyone. My name is Alex Filipenko. I'm a professor of astronomy at the University of California at Berkeley, and it's my pleasure to be the moderator of this discussion among the physics, math, and astronomy people. I'll briefly introduce them and then ask each of them a question. And then by that time, we hope to have the live chat going and lots of questions from the audience, keeping a majority of the time used up by questions from you. So I'll ask each of you to just wave when I say your name, and we'll get started. We'll get started that way. We've got David Coulter from UC Santa Cruz, a fifth-year student in astrophysics. Let's see. Spencer Everett, a fifth-year student at Santa Cruz, also in astrophysics. Elon Rosen, a sixth-year student at Stanford, working on quantum systems. Luis Perez, a first-year master's student at San Francisco State University, and he'll tell us about his undergraduate project. We've got Stanford fifth-year astrophysics student William DeRocco. Maggie Thompson, whose year I didn't quite catch, but Santa Cruz, another astronomer. She told us about outgassing from the meteorites in the main session. And also we've got, let's see, Kevin Yang, fourth year Stanford student, working in physics and mathematics. And then we have, last but not least, Cesar Meza, a second-year master's student at San Francisco State University. So those are our scholars. Only one of the scholars couldn't make it, but we're very pleased to have these 8 scholars with us. So I just wanted to start by asking each of you to comment on how this past year has been for you. How has the pandemic affected your research? How were you able to get things going? Did it not affect you? Were there people or institutions or facilities that really helped you out besides Zoom, of course? And were there any silver linings actually to having all this be present? Not that we wanted to have a pandemic of this sort, but sometimes you can make good things come of it. So I'll just go in the order that each of you are on my screen. You can unmute yourselves. And Kevin, tell us a little bit about how things went for you this year.
Yeah, thank you, Alex, for the introduction and moderating. So I think I'm pretty lucky in that I didn't need to go into lab or anything to do my research. So I could pretty much do everything at home and talking to everybody on Zoom. And it was good and bad for productivity to sort of just be at home pretty much all day to just work. One silver lining actually that came up, because I didn't have to be anywhere in particular, I actually got to live in a few different places over the country. And that was very refreshing, both work-wise and just sort of personally.
Well, that's great to hear. And you were able to travel to these different places without getting on an airplane for a while or something, or?
It was all driving. I drove all over the country. It was pretty fun.
Yeah, nice time to take a road trip.
Yeah.
But yeah, in your line of research, which we'll get to in a few minutes here, it seems like, not having a lab with animals in particular to take care of, you didn't have some of the concerns that I think our friends in biology in particular had to deal with. So that's great.
Sure.
Well, thank you, Kevin. Spencer, how about you?
Hi. It probably shouldn't have, in principle, made too big of an impact. So I work as part of a big collaboration galaxy survey called the Dark Energy Survey. And so, unfortunately, I was very familiar with Zoom ever since the start of grad school before the pandemic. So there were about 30 institutions from 4 continents. So we were already kind of used to the remote life. So I could do a lot of my work just through programming or simulations or Slack remote as usual. But by far my favorite part of the PhD and of the science was getting to meet with all of those people at collaboration meetings and workshops or just driving up to Stanford, at small distances, big ones, and getting to know the people and work with them together. All of our best ideas for papers and measurements came from being in the same room over a coffee break or over dinner. And so I think a lot was missed through that. So the work was able to get done, but I think a lot of the joy I found in science was missing without getting to meet more in person with the other astronomers, I'd say.
Yeah, I can totally understand and sympathize with that. We're in very similar fields, and it was the same for me. I should mention, though, that probably CTIO, the Cerro Inter-American Observatory, where the measurements, where the data for your research were taken, that was closed down for a couple of months, right?
So we were very fortunate. DES finished measurements just a little bit before the pandemic. So there's a lot of follow-up measurements using the camera that we built and essentially donated to the 4-meter telescope there. So that affected a lot of the follow-up spectroscopic measurements or of other legacy surveys that are doing similar things, but we had finished all of our observations.
Yeah.
So luckily I'd gotten to go down a couple of times before the pandemic hit.
That's right. In your presentation, there's that photo of you next to the 4-meter Blanco telescopes. That's very nice. William, how about you and your research?
Yeah, so I mean, I'll echo a lot of what was already said, which is just that there were pros and cons for sure in terms of productivity. I found it was a good time to finish existing projects because those were already something that you understood and you just had to sit down and actually get it done, write the paper, etc. What I thought was very difficult during pandemic and during lockdown was sort of any degree of project generation, right? Which this is sort of something that happens to the point that was just previously made over coffee or something. You just start talking about something with someone and say, oh, that's a neat idea. We should think about that some more, right? And so that was really lacking. And in my personal opinion, that's the most exciting part of any project is the initial phases where everything, you're starting to really dig into what interesting physics there is to do there. And so that was difficult, but again, the silver lining was that I was able to finish off a bunch of things that otherwise might have fallen by the wayside in favor of the exciting new prospects.
Yeah, there's always those fun brainstorming sessions by a chalkboard or a whiteboard where everyone's sort of throwing out ideas and all that kind of stuff, and we couldn't physically be together. So that part of the research aspect was lost.
No, I miss getting to talk to someone next to a chalkboard more than I can possibly say.
Yeah, very good. Well, sounds like you made the best of it, though. David, how about your research?
Right. So I work primarily in searching for EM counterparts to gravitational wave sources. So LIGO shut down as a part of the pandemic, and that definitely truncated, our search. We kind of feel sometimes like we're storm, watchers. We're hopping in the van and going to the, observatory and trying to catch things as they happen. So that shifted the focus to analysis, analyzing all the data that we had taken before, because we rely a lot on the telescopes in Chile, and they were shut down. On a personal note, though, we were also vacated because of the fires during the pandemic. And that was really rough with the family. I have a wife, and now I have 2 children. At the time, I had a 9-month pregnant wife, so we were looking for places to both stay safe from the fires and deliver and stay safe from COVID at the same time. So it was quite an intense journey to finally get back to Santa Cruz and get back to science.
Wow, what a wild time. Well, congratulations to you and your wife on the 2 kids and a successful delivery of the second one. But yes. Yeah, well, wild time. By the way, I have a graduate student who's, earlier in his development than you are, and he too wanted to work on LIGO type things. But, given that it probably won't turn on until sometime late in 2022 or 2023, we've redirected his thesis project. So, okay, Cesar, do you want to say a few words about your research?
Yeah, so my research is in pure mathematics, and so I don't necessarily need any special equipment, or I don't need to walk into a lab every day to conduct my research. And so similar to what everyone else has said, the large difference is the quality of collaboration that I experienced during the pandemic. We still have Zoom and online platforms to collaborate and, digital whiteboards, but the quality is not the same as, working together in person on a whiteboard or a chalkboard and, having a problem up on the board all day, taking a break, walking away, talking about other things, and then coming back to the problem. We didn't necessarily have that during the pandemic. And one silver lining is that being able to go to conferences was more affordable because it was remote and online. So I was able to attend more conferences than I usually would. And that, kind of helped spark some ideas towards my project.
Yeah, that's great. Well, the mathematicians, I think, are able to deal with this situation better than almost anyone else, because even observational astronomers had to deal with observatories that closed down or whatever. But great that you were able to do so well, Cesar. Luis, how about you?
Yeah, I mean, I think the transition I made from undergrad to San Francisco State was probably the bigger struggle, and kind of pairing with like a research advisor to actually start doing research as of state, because I'm a first-year master's student, was something that I felt like was going to be a struggle when making that transition. But I want to give the thanks to San Francisco State, because they do have a lot of support programs, and they actually this year they started the first cohort of the BAM program, which is geared for master's students in mathematics, to help them and support them transition into a PhD in mathematics. So programs like these were very beneficial in making that transition during this time. And because of that, I've been able to pair with the research advisor, start doing some work on that potential master's thesis, and also, meet with students that, I can study with and talk about these ideas with.
Yeah, I hear you. First year college students, freshmen, couldn't be on campus. First year graduate students couldn't be on campus. And so it was difficult to meet their professors and get started on research projects, but it sounds like you did quite well, actually. Okay, good. Maggie, you're next.
Yeah, so I do have lab work. So obviously that was certainly affected in the beginning times with COVID. Our lab closed sometime in March and then reopened back in the summer. Luckily, I was working on a referee report for a paper, so that timing was fine. I was still able to work on that and get stuff done. I will say another potential silver lining was also that the labs were pretty quiet and still are. Normally, they are really hustling and bustling, which is certainly great. Often, it's really nice to have conversations, but with doing some lab work, it's really nice for it to be very, very quiet. Although my biggest downside is I really miss our office. Dave and I share an office on campus. And so it's really sad that we don't get to be there, but hopefully sometime in the next few months or in the fall, it will reopen.
Yeah, now when you went to the lab to do your research, were you under the restriction of one person per 600 square feet or something like that?
It really varied a lot. Initially, yep, it was one person at a time, twice a week COVID tests. Now it's maybe 3 people in the room at a time. It was actually a little funny too, because actually the labs have incredibly good air circulation. So it's actually probably a really safe place to be compared to, say, the grocery store. So I felt pretty lucky and definitely felt very safe once I was in there.
Yeah, but the equipment could be run by just one person, by you. You're just sitting there vaporizing a meteorite.
Yep, exactly. And the unfortunate thing is if, something goes wrong or you need a question, you can't just walk down the hall to the person that normally is always there. You really have to schedule things a lot more and be a lot more thoughtful about it.
Yeah, right. Great. All right, Elon, do you want to tell us about how things have affected your work?
Sure. So similarly to Maggie, I work as an experimentalist in lab, and we also were shut down for a number of months. Since then, we've slowly been ramping back up, but there's been a number of infrastructure challenges during that period, and it's still, things are just slower. Like Maggie said, air circulation is very good. I do a lot of work in the clean room, which has, I think, the best the cleanest air you can get anywhere. So that's, I guess, a funny silver lining. But to echo others, I think the biggest challenge hasn't been infrastructure, it's been community. I think that science is ultimately a human endeavor. It's by humans, for humans. And to be removed from our community has been very difficult. It's difficult to be creative. It's difficult to be passionate and enjoy your work. And it's difficult to mentor others when you're not with them. And I think everyone all over the world can feel that. There has been a couple silver linings, like Cesar said, conferences and being able to connect with people all over the world. That's been wonderful, and I think that's going to continue after the pandemic. Another thing is there's a lot of questions that I've been able to ask that I wouldn't normally have bothered to ask. Sort of a reworking of our lifestyle. Why do we sit in lab for 8, 10, 12, 14 hours a day? And so being able to just randomly get up in the middle of the day and take a walk and not be accountable to peer pressure, but just be accountable to my own needs. That's been an interesting shift in mindset.
Yeah, those are very good points. Going back to the conferences, I think that really is a silver lining in that there were many conferences that I didn't attend because there was not sufficient interest on my part to really spend, 5 days going there, participating, blah, blah, blah. But there were parts that I would have been interested in, and now I can attend those via Zoom and still go on with my normal life. The other thing is that we can really reduce our carbon footprint by not going to so many meetings, especially ones that are in locations that you might not really desire to go to. I mean, there are some conferences where, we go in part because it's a very attractive location and you can explore the area before or after. But, if it's in a region that's not all that attractive to me, I'd rather not increase the carbon footprint and just remotely participate. So I think I agree with you. At least partial remote participation is here to stay. Well, I invited the audience to start typing their questions, and they haven't typed any yet. But I always have lots of questions, and I have one that for each of you that I can sort of ask, and maybe you can comment on them. And meanwhile, I'll monitor the chat room for questions from the audience. But we'll start with Spencer, who did a large-scale survey of the distribution of galaxies in the sky using this amazing dark energy survey. But Spencer, although redshifts and hence distances are obtained through spectroscopic means for some of the galaxies, it's a small minority of all the galaxies. So how can you study the growth of large-scale structure by just using the positions of the galaxies, not knowing their redshifts, not knowing their distances?
Right. So that's a really good question, and is by far the biggest uncertainty in any work done through what I used to call a photometric galaxy survey rather than spectroscopic. So a big part of my dissertation work is exactly helping answer your question, which is we really can only get very noisy guesses of how far away they are rather than a precise redshift estimate. We just guess and try to give it an accurate uncertainty. And so we get the initial guess by looking at the colors, as things further back in time tended to be producing stars that are bluer. Over time, star growth slows down, so they're redder. And then on top of that, things that are further away are redshifting away from us. So there's this high dimensional color aspect that gives you information you need, but there's all this additional noise from the measurement and just from projection of other galaxies. And so one of the ways we deal with this is through my work, we inject galaxies where we know what the redshifts are exactly from other spectroscopic surveys. I sprinkle them in over the real images, and we just rerun the full measurement pipeline like we would with real data. And I now know the difference between what we think the redshift or the distance to it should be versus what it actually was. And so we can accurately characterize how wrong we get those and how often. And so that goes into our cosmological measurement.
I see. And do you get, from the 1% subset or whatever is of galaxies for which you get spectroscopic redshifts, can you then extrapolate to draw general conclusions about the whole sample if the ones for which you got redshifts are at all representative?
Right. So that's the other huge part. So there's like 6 main uncertainties that go into the estimation of the photometric redshifts. Mine is one of them in understanding this measurement error. There's all sorts of other contributions. And like you said, the bias coming from using a small sample of the whole universe, this like cosmic variance bit, that is accounted for in the analysis. And so essentially, since we don't have that, what you really do is you just try to guess how broad the errors should be, given the fact that you use a finite. So we have various ways of simulating what we think that error contribution is. So it broadens the errors.
Yeah. Okay. Well, that's great. Let's move to David Coulter. David, your work on the colliding neutron stars was very interesting, but as you know, almost all of the events detected by LIGO and Virgo have been merging black holes. Why would you expect merging black holes to produce an electromagnetic signal in any of the cases?
That's a good question. I think there's a couple ways to think about it. The first is just to take what you're saying and think about 2 black holes in the void. You're right. There's not necessarily anything that when they merge, you'd expect to see something. However, if there's something around those black holes, like accretion disks or some kind of gas, that when they do merge, something outside the event horizon can be shocked or excited. You might be able to see some light associated with that. What color that light is, how bright it is, how it changes in time, are all going to be very dependent on the model you use. But then the other part of this is, why do we look? It's because no one's ever seen it before. And if you did catch something, if you did see something like that, you could know something very deep about both the progenitors, where they're located in the galaxy, can tell you how they formed, how they got to be in that place. And also this standard Siren measurement, which you could make if you actually connected the EM counterpart to a gravitational wave source. So the standard Siren is another way to measure the local expansion rate of the universe. So basically it's a quantity that says, how far away do you go and how fast is the universe moving at that distance. And so the gravitational waveform itself will give you a luminosity distance. And then if you could find the actual source in a galaxy and get that redshift, the same quantities that Spencer's talking about, then you could directly measure H naught, the Hubble's constant. So there's a lot of really good reasons to look for binary black holes that are merging in deep space. And hopefully someday someone will find something. Yeah.
Well, let's hope LIGO Virgo turn on sometime soon. Do you have an estimate of when this might happen?
The turning back on?
Yeah.
Yeah, 2022, I think. Is when it's
your thesis will be largely done by then, right? So
yeah, that's right.
Yeah.
I do have we do have some proposals to chase some counterparts if they're discovered. So
Right.
yeah.
Okay. I have a question for Maggie. Maggie, you studied mostly the chondrites, but of course the stony meteorites may have less gas per meteorite, but so many stony ones came in and made Earth. Wouldn't you expect there to be a lot of gas in total from the stony ones? And how might you account for that as part of the composition of our atmosphere?
Certainly, yeah, that's a great point. So there's several ideas here. One is you could expect that maybe you get a lot more of your volatiles later on. So after the planet initially forms, you might have some sort of late heavy bombardment period where you would expect more of these ice-rich planetesimal-like bodies, the carbonaceous chondrites, like what we studied, that then somehow get perturbed to the inner solar system and can provide some water. But also that's something that we want to figure out with these experiments. That's certainly true that a lot of these stony meteorites don't have as many volatiles compared to some of the other ones, but it's something that experimentally has not been quite looked at as extensively or within this framework in mind. And so that's something that we want to check. For example, people really think that, as I was mentioning in the Q&A in the main session, N-statite chondrites are these really relevant and exciting types of chondrites that seem to match some Earth values in various, if you look at different isotopes, they're a pretty good match. And so the idea is we want to look at those because you expect those to not be quite as volatile rich compared to the ones that I looked at in my first study, but it's something we want to certainly see. And so stay tuned. Yes, that's a great point.
Okay, well, yeah, good luck with that research.
Thank you.
So I wanted to ask Luis to give us an example of how the error correcting code research that you're doing, Luis, can apply to a magic trick. Can you tell us one magic trick for which your research is applicable?
Yeah, that's actually, I think, the main result that I was able to actually publish. It was just like implementation of a magic trick, make it more, I guess, in general, it makes the trick more impressive. But the trick is called the parity card trick. It's a trick with cards, or using cards, and the idea is the kind of language that the magician understands, it cannot be interpreted by the audience, but this language it uses concepts of error correcting codes, this idea of like parity, where you take a message, and when you send the message, you want to encode it by adding parity bits, and that, through this kind of language, this magician is able to perform the magic trick without the audience really understanding what's going on. And so my implementation of this magic trick has to do with a magician and an apprentice. So now they're able to communicate in a language where using error correcting codes, the audience is not able to understand.
Okay, well, I'm always, I love magic tricks, not that there's magic, but I love trying to figure them out. And I swear, when I'm in front of a good illusionist, I watch with an eagle eye, but I still can't figure out how they do most of their tricks. So don't want to learn too much from you right now, because I want to figure it out myself. But if I get too desperate, I might contact you and have you tell me how they do some of these tricks. William, you're trying to find, dark matter particles from supernovae. But how do you know that a xenon detector, or even, gamma rays that are detected, are coming from a particular supernova, like in my background here? How do you know where the dark matter particle came from, if it's ever detected?
Yeah, great. So that's a very good question. So one of the really interesting elements of the research that I did, specifically on sort of sub-Jev, so, not quite your wimpy dark matter, about a 3 orders of magnitude lighter. This kind of dark matter can be produced copiously in supernovae, but it's very strongly coupled. And because of that, when it escapes, it will escape with a semi-relativistic velocity, all right? And so that means that, unlike the neutrinos, which all arrive in sort of a 10-second burst from a given supernova, these particles will arrive over, of order the light travel time from the supernova to Earth, right? And so that's, that's several thousand years if these things are going off in the center of the galaxy. But what's great about that is that with 2 supernovae going off roughly 2 supernovae per century in the galaxy, means you have a lot of overlapping supernovae emissions that are all arriving at Earth at the same time. And these are observable in things like a xenon detector, which is built from a much, much heavier particle, because they are semi-relativistic. They're moving very, very quickly. And so they can compensate with their high velocities to have a momentum comparable to sort of a cold cosmological WIMP. And you ask a good question, which is, okay, so fine. So let's say a xenon detector sees something. How are you ever going to tell them apart, right? And one of the critical ways that you can do it is actually with directionality, because any sort of WIMP particle would appear to be coming from the direction of the Cygnus constellation, just due to our galactic rotation as we move through the halo. However, since most supernovae are going off at the center of the galaxy, any signal from supernova dark matter would be coming from that direction, which is pretty much perpendicular to where you'd expect a WIMP signal. And so with directional detectors, you would be able to pretty effectively discriminate these two populations.
Okay, thanks. That's really interesting. You know, I wish all of you luck. I've been in this field for decades now, and we still haven't detected even a single clear example. Maybe the Dama result in Italy, but that one is, you know, kind of, yeah, that's the reaction I get from the pundits that I talk to. They're not convinced. So good luck to you, you know.
It's out there. It's out there. We'll find it eventually.
Yeah. Right, right. Kevin, so you studied, you know, random growth models, stochastic models of, you know, growing bacteria in petri dishes and things like that, and in coffee cups. But what if there are known instabilities, like Rayleigh-Taylor instabilities that occur when there are different densities in a gravitational field, or Kelvin-Helmholtz instabilities when things, you know, fluid layers are going past one another? Do any of your models include room for these known instabilities, or are you just looking at the random stochastic growth?
That's a great question. So the models that I've been studying for the past year or two, they're mostly just about fluctuations in these sort of relatively stable models. So sort of materials or situations where you have a lot of impurities or a lot of imbalances aren't described by the models that I'm researching. However, sort of if you look close enough so that sort of things look stable. So if you have two phases that sort of disagree and you look sort of in each phase, you do sort of see these fluctuation statistics that I'm studying. The question mathematically is, why do you see these? And the interesting thing here is that the mathematicians and the physicists actually have disagreeing opinions as to where these things come from. And that's sort of the story.
Right, and you're looking to see whether there really is a universal equation that describes this random growth, right?
Yes,
And,
exactly.
And mathematicians and physicists still disagree about whether this universal thing really does or does not exist?
So they agree that it should exist. The sort of interesting thing is that the reason why the physicists believe it exists, if you sort of follow their reasoning, you actually get numbers that don't agree with lab experiments.
I see.
Which means that there's something interesting that's happening. There's sort of a story to tell, and that's sort of the problem.
Interesting. Well, good luck to you.
You.
Two more. Elon, in your work, you are studying the electron transport in certain materials, but you mentioned chiral electrons. Can you explain to the audience what chiral electrons are?
Sure. Yeah. I mean, so the word chiral is a bit of a buzzword, but it stands for a certain type of symmetry. So typically in some material, if you have an electronic state available, say an electron's going forward in the x direction, then there has to be another equivalent state where the electron is going backwards in the x direction, and that reflects some symmetry in the material. And there's different ways to break symmetry. And in particular, the system I study is called chiral, and that means there's sort of a circular transport, as if the analogy we use is, imagine there's a one-way road going around an island sort of along the beach. So you can only go in one direction. So if the island is a material, then this road is sort of the only available electronic mode.
Sorry, I was muted there. Yeah, that's and the material imposes this restriction that there's only one way.
Exactly.
Yeah.
Yeah. So the material I work with is called a topological material. So traditionally, materials have been characterized in terms of phases, which are really just symmetries, right? So if you freeze water, it turns from a liquid to an ice, and the symmetry changes. Liquid water is very symmetric. When it turns to ice, it turns into a crystal. So there's no more translational symmetry. There's only a discrete translational symmetry. but people realize that there's actually a different way to characterize materials, which is in terms of topology, which is the study of knots. And there's a way to actually turn the electronic structure inside materials into something that can look like a knot in these materials. And so this chirality or any other interesting electronic properties, it's a confluence of the topology of the material together with its symmetries.
Well, that's fascinating. And the electrons travel along the edge, you were saying, I think, right?
Exactly.
Yeah. Okay. And then last but not least, we have Cesar. Cesar, I understand Euler's polyhedral formula, really amazing. Vertices minus edges plus faces equals 2. I'm not sure that I was aware of that. So vertices, edges, and faces are all flags, right? And in a higher dimensional space, the next thing would be, I'm sorry, that would be the flag, is that right? In one higher dimension?
So a flag is a collection of those objects. So, you know, if you take a vertex and it's placed inside a edge, and then we have that edge inside of a two-dimensional face, that collection of subfaces or faces is called a flag. So in higher dimensions, I can have like a one-dimensional edge inside of a four-dimensional, you know, face of a polytope, and that would also be a flag. So a flag is just a collection of faces.
Okay, it's the collection then, right? But in a Platonic solid, you don't have that fourth dimensional vertex-like analog, right?
Correct.
Yeah, but you're thinking of now about a higher dimensional space where you have points, edges, faces, and then one higher thing, right? Volumes, basically, right?
Correct, yeah.
Okay, and have you found an equation, or do you guys think there is an equation in higher dimensions that corresponds to Euler's polyhedral formula?
Yeah, so there, it's related to topology, where you just alternate the sum of those types of objects. So you take the vertex and you subtract the edge, you add a face, you subtract a four-dimensional face, you add the fifth dimensional, and you know that relationship remains the same. So the type of questions that I'm interested in now is we have these things called face vectors, which kind of counts the number of vertices, edges, and faces, and so on for a particular polytope. And so we can count that off of any polytope. And so what I'm looking at is how can we take two different polytopes and somehow, you know, this idea of multiplying them to create a new polytope, and how can we I guess compute the face vector of that new polytope using information from the two that we multiplied together. And so that's what I'm looking at now.
Mm-hmm. But the relationship will not equal 2 the way it does in 3 dimensions for a Platonic solid or something like that. It'll equal some other number.
Yes, it'll equal a different number.
But we don't know what that number is yet, right?
I believe, if I remember correctly, depending on how you rearrange the terms, it should equal 1, either 1 or 0, depending on how you arrange the terms.
But presumably that depends on the dimensionality of your space.
I guess the way that you alternate the terms does, yeah.
Okay. Well, listen, congratulations to all of you on your fascinating research. You make the ARCS program proud. And although we had a bit of a glitch and there weren't questions from the audience, I hope my questions were worthy of your attention. And so thank you for participating today, and best of luck in your thesis research.